The next alkene reaction we're going to talk about is the hydroboration-oxidation. This reaction was pioneered by H.C. Brown at Purdue University. And for his work in this chemistry, he received the 1979 Nobel Prize in Chemistry. Let's start by recalling a reaction that we learned previously in this chapter, where you can take an alkene and add acid and water and do a hydration, where we add H and OH across the double bond. And we learned that the OH will add to the more substituted carbon, and this is termed Markovnikov addition. So what we're working towards is having a toolbox of reactions such that we can start with something simple and build a more complex molecule. But as you're building molecules or synthesizing molecules, you have to be able to put things in the right place. So what if instead we actually want this OH on the less substituted carbon of the double bond? So that's kind of the question we're asking, is how could we accomplish that? Same double bond. How do we get this? And this would be termed an anti-Markovnikov addition. Here the hydrogen goes to the more substituted carbon, the OH to the less substituted carbon. Well, in general, when you're trying to get a different product, what you need to do is change the mechanism. And we can change the mechanism by changing the reagents. And what reagents do we need to do this? We're going to use BH3, followed by a second step with sodium hydroxide and hydrogen peroxide. And the BH3, that's the hydroboration step. And we can see this written a couple of different ways. You might just see BH3 written. You might see it written as a THF complex, meaning it's just complexed with the solvent. Sometimes we even see it written as B2H6, where the BH3 forms a dimer. If you see any of those reagents, immediately you should think of hydroboration. The second step, where we use H2O2, that's the oxidation. Boron is sort of an interesting element. It's really quite special because it's never stable, or you can think of it as it's never happy. We can see this if we look at the structure of BH3. Boron does not have any lone pairs. It just has the 3 bonds to the hydrogen. And if you look at the structure of this, we have the central atom boron, and we have 3 hydrogens, all in a plane. Why? Because the boron is sp2 hybridized, because it just has 3 groups around it. Something that is sp2, we know will have a p orbital. So there's also an empty p orbital on boron. This is a lot like a carbocation in that the atom is electron deficient. Boron only has 6 electrons, so it lacks an octet. The one thing it does have that helps in terms of stabilization a little bit is that it has a formal charge of 0. So just think of this as pretty similar to a carbocation. So then you might wonder, well, what if we add a 4th hydrogen to the boron such that it then has an octet? So let's do that. Let's draw boron, For hydrogens, it is now sp3 hybridized and trigonal or tetrahedral. But if you calculate the formal charge of this, boron is in group 3 minus 4 bonds minus 0 lone pair electrons, negative 1. Boron now has a negative formal charge. So the good is that it has 8 electrons, it has an octet. The bad is it now has a formal charge. So it really can never be happy. It's either 0 charged and lacks an octet, or it has an octet and carries a formal charge. So that's what makes it have sort of a special reactivity. I mentioned before that boron is often written as a BH3-THF complex, and that's because it's most commonly sold as a solution in THF, tetrahydrofuran. If we draw out the structures, you can see the purpose for this. So here is BH3. I'm going to write it as H3b. And we know that the boron is electron deficient. So it does want electrons. Well, the structure of tetrahydrofuran is this 5-membered ring with an oxygen. And what's this oxygen have? Lone pairs. So what that will do is it will coordinate to the boron, donating some of its electron density to the boron, helping to stabilize it. So this is the THF, and this is often written as BH3 THF, and it's a complex. Let's walk through an example hydroboration reaction, and we'll talk about the mechanism. So here we're starting with an alkene, and we're adding the BH3 THF to do the hydroboration, sodium hydroxide, hydrogen peroxide to do the oxidation step. This is a 2-step process, meaning we basically do step 1 and let the reaction stir. Then when that step is complete, then you do step 2. So a big important thing to keep in mind is these are 2 separate steps. Everything isn't mixed together at once. So if you were to write this reaction like this, that implies everything is mixed together at one time. That would not give you the desired product. That's incorrect. So let's predict the product for this. What you want to do is, again, look at the 2 carbons of the alkene, here and here, and figure out which one is more substituted and which is less substituted. This carbon has 2 hydrogen. This carbon has 1 hydrogen. Because the hydroboration is anti-Markovnikov, the hydrogen adds to the more substituted side this time, the OH to the less substituted side. So when I draw the product, the OH will go to this carbon. The hydrogen, you don't have to draw it in, but I will for clarity right now. It goes to this carbon. So again, that's anti-Markovnikov. Meaning the OH goes to the less substituted carbon. Also, an important feature, there's no carbocation rearrangement because there's no carbocation in the mechanism that we'll see here in just a second. A common question that I get is, well, how do we know if something's going to rearrange or not? It's really pretty simple. You only get carbocations in your mechanisms when you're reacting an alkene under acidic conditions. So at least for this semester, you can hang on to this statement. If it's an alkene and an acid, there's a carbocation in the mechanism, you have to watch out for rearrangement. When acids aren't involved, you don't have to worry about them. So let's walk through the mechanism. We're going to look at the hydroboration step because this is really the reaction that's happening with the alkene. Here's our alkene, and what happens is the BH3 will get into close proximity. And then we're going to draw two arrows because this happens in a single step. The double bond attacks the boron. The double bond's a nucleophile. The boron is electron deficient, so we know it's the electrophile. And then at the same time, rather than form a carbocation, the hydrogen from the boron adds to the carbon of the double bond, the more substituted carbon. So what do we get? We end up with a bond to BH2 and a bond to the hydrogen. Just to kind of help you track electrons and where things are going, I'm going to show you a step that doesn't actually happen. So I'm going to draw it in gray just to say that it's kind of a figment of our imagination here. But think about what would happen if the double bond just attacked the boron first. If that happened, you would form a bond to the BH3. So now you have 4 bonds on the boron and a negative charge, and you would get a carbocation. And then one of these hydrogens would go to the positive charge and take you to this product. Now that intermediate does not form, this doesn't happen. This is in reality a single step. But it does show why the hydrogen goes to the more substituted carbon. This carbon is the one that can have the most partial positive character. So that kind of explains the regio selectivity of why the boron goes to the less substituted side, the hydrogen to the more substituted side. Again, I'll make an important note here. This does not really happen. From there, now we do the oxidation step. Where we add NaOH, H2O2, and what happens in this is a fairly complex pattern of mechanisms that, right now we're getting started on mechanisms, so I don't want to overwhelm you. Also, our focus right now needs to be reactions with alkenes and their mechanisms. So for now, just suffice it to say this boron gets oxidized to an OH. And there's your product.